The mole in a nutshell. So what exactly is the mole? Well, the mole represents different values. It's a way of comparing different chemicals against each other. So if you're trying to compare carbon versus lithium, the most common way to do it is to compare it in terms of moles. How many moles of carbon you have and moles of lithium. The reason is because the mass of those two chemicals are different. Lithium would have a mass of 7 grams per mole according to the periodic table. Carbon would have 12 grams per mole. So in order to compare these two chemicals together, the best way to do it is go to moles. And there are 3 different values you need to understand in relationships regarding the mole. The first relationship you need to understand is the mass of all the elements in the periodic table are equal to exactly 1 mole. So all those numbers below the symbol, those are all equal to 1 mole. So 1 mole of carbon is 12 grams per mole. 1 mole of nitrogen is 1 grams per mole. Everything is equal to 1 mole. 2, it's equal to a number. So when you think of the mole, numerically, the mole is equal to 6.02 times 10 to the 23rd of anything. You could have 6.02 times 10 to the 23rd dollars, pennies, atoms, molecules. It's pretty much wide open what you could relate it to. It's kind of like when you think of a dozen, you think 12. When you think pair, you think 2. So when you think mole, this number needs to pop up in your head because that's usually the most common way to use is atoms and molecules. That's the most common relationship that this would be equating to. 3, there are exactly 22.4 liters in 1 mole of gas. This only applies to gases, nothing else, not for solids, not for liquids, gases only. So it turns out that 1 mole of any gas, whether it's an element or a compound, is equal to exactly 22.4 liters. So let's start out with molar mass. So what is molar mass? The mass of a single mole of an element or compound. The units for it are grams per mole. So for elements like carbon, the molar mass is 12 grams per mole. Where did I get 12 grams per mole? It's the number right below. And for our purpose, we're going to round the numbers to the nearest whole number. So carbon's 12.01. We're just going to call it 12, just to make it a little simpler. For compounds, it's the mass of all the elements added up. So for CO2, for example, carbon weighs 12, and you have 2 oxygens. So how much does oxygen weigh? Well, each oxygen weighs 16, and there's 2 of them. So that's 32. So to get the molar mass of a compound, you need to add up the masses of the elements in the compound. That's the one little catch to it. So in this situation, you get 44 grams per mole for the molar mass of the whole compound. So all these are equal to exactly 1 mole. And you can see the quantities or the visible quantities are different. This looks like there's a lot more than here. This looks a little bit more than this. These are all equal to 1 mole. So even though the quantity in terms of grams or the volume they take up may be different, they all equate to exactly 1 mole, including this balloon. There's exactly 1 mole of gas in this balloon. And because it's a gas, you know that this 1 mole is equal to 22.4 liters. That's the relationship we're going to get to in a second. So all the mass in the periodic table equal to 1 mole. So sodium is 23, magnesium is 24. We're going to call it 24 instead of 24. We're going to skip the decimal for our purposes. Aluminum is 27, silicon is 28. The only one you may want to keep as a decimal is chlorine. The actual mass is about 35.45. So we rounded to 35.5. Typically, you'll see a lot of resources use as 35.5. If you round to 36, not the end of the world, but this is the one that you may want to consider keeping in decimal form. Everything else, krypton's 84, argon's 40, neon's 20. Just round it to the nearest whole number. Skip the decimal. So let's try some questions. So how many grams are in 1 mole of aluminum? So if you look in the periodic table, the mass of aluminum is 27 grams. So it's asking for 1 mole. So what would 1 mole of it weigh? 27 grams. What if I have 2 moles? 2 times 27 grams, which is 54. So the quantity of moles you have, you just multiply by the molar mass, and that's the grams you have of that substance. Case in point, look at sulfur. So I have 64 grams of sulfur. So you look in the periodic table, sulfur's molar mass is 32, but I don't have 32, I have 64. So how do you do this? We need what's called a T-chart. The principle of a T-chart is whatever you're given goes in the upper left-hand corner and you make a T. The goal is to go from one unit to another. So I want to go from grams to moles. That's the whole point of this question, right? They're starting with grams and they want to go to moles. So what you want to do is put the unit you're looking for on top, the unit you're starting with on the bottom. So the question is, where do I get these numbers? Because these are just units right now. The periodic table. Because we're dealing with molar mass, we're going to use the molar mass in the periodic table, which is 32 grams for every 1 mole. whenever you do molar mass calculations, going from moles to grams or grams to moles, it's always going to be 1 mole of that substance. That's always the requirement, so keep that in mind. So mathematically, what do? Multiply the top numbers together, 64 times 1, divide by the bottom number, which gives me 2 moles. So I have 2 moles of sulfur, which means the answer is 3. All right, what about calcium carbonate? What's the molar mass? Well, calcium is 40, carbon is 12, each oxygen 16. 16 times 3 gives me 48. So I just have to add up the mass together, and that's how I get the molar mass, which as you can see is 100 grams per mole. So once again, for compounds, all you have to do is add up the mass of the elements in the compound, and you get your total. The complicated ones are the ones that have parentheses, because now we got to distribute this 3 to everything inside the parentheses. So 3 times 14, which is 28, 32, 42. You have 12 hydrogens, 3 times 4. You got to distribute it 3 times the subscript. Here the subscript was 1, that's why it's just 3 times 14. So this is 1 times 12, which is just equal to 12. Phosphorus, just one of them, no distribution required. And then oxygen, we have 16 times 2, which is 64 grams per mole. So we add all the mass together and we get the total mass of the compound, which is 149. So the only complicated ones for molar mass are when you have parentheses, because you have to distribute the number on the outside to everything on the inside, and then just add up the numbers again. All right, moles and Avogadro's number. So this is that value that we're talking about, 6.02 to the 23rd. Just to understand how big this number is, that's how big the number is. That's a lot of zeros. So this is a huge number. So as a result, this is how many atoms or molecules are going to be in most elements or compounds from the periodic table or that we see in nature. So in chemistry, we use it to indicate the number of atoms or molecules. So for example, if we're talking about single elements, we call it atoms. So 1 mole of carbon, 6.02 to the 23rd atoms. 1 mole of lithium, still 6.02 times 10 to the 23rd atoms. What do we talk about compounds? What's the difference? For compounds, the only difference is same number, we just changed the wording to molecules. This is a molecular compound. This is not ionic, so that's what we call molecules. If we're talking about ionic compounds, they're called formula units. That's the most common way to refer to them. But we're dealing with molecular compounds here, so for that, just use the word molecule. So that's how many molecules are in 1 mole of CO2. Once again, same number, different word. 1 mole of nitrogen dioxide, same thing, 6.2 to the 23rd molecules. So let's try some questions. How many molecules are in 1 mole of CO2? Well, we know that 1 mole equals to 6.02 to the 23rd. So real simple. This one takes almost no time. There's our answer. So you have 6.02 to the 23rd molecules of CO2 in 1 mole. What about how many atoms are in 64 grams of sulfur? A little bit more work, because first we need to do is go to moles. We can't go from grams to atoms directly. So how do we do that? Well, first we want to go to moles. So we did this calculation before. We set up our T-chart, we put our molar mass, 1 mole, and we get 2 moles. So some of you guys can do this in your heads. Guys say that 2 times 6.02 to the 23rd gives you 1.2 times 10 to the 24th. Other of you guys may want to just set this up. So I'm going to set it up. T-chart again. Remember whatever you start with. So I'm going to start with moles because I could go from moles to atoms or molecules. I just can't go from grams directly to atoms or molecules. So 2 moles, there's 6.02 times 10 to the 23rd atoms, because it's a single element, in 1 mole of sulfur. Once again, you notice it's just always 1 mole for molar mass, 1 mole. That's the common trend. So keep that in mind. When you're doing this T-chart, it's always going to be 1 mole of something, top or bottom usually. All right, so 2 times this gives me 1.2 times 10 to the 24th atoms. And then going to the next one, how many atoms are in 12 grams of carbon? Well, for this one's pretty simple. You know that 12 grams equal to 1 mole. We could do a T-chart, but you know that's the relationship. So how many atoms are in 1 mole of an element? Well, what it always is, 6.02 to the 23rd. That's how you would do it. Molar volume, on the other hand, is only if there's a gas. So there's 22.4 liters in every mole of a gas, whether it's an element or a compound, doesn't matter. So 1 mole of helium, 22.4 liters. 1 mole of fluorine, 22.4 liters. 1 mole of carbon dioxide, you guessed it, 22.4 liters. So everything is equal to exactly 22.4 liters for 1 mole. Looking at it from a relation standpoint, you have 1 mole of carbon here, so that means there's 6.02 to the 23rd carbon atoms. That's how many atoms are here. There's 12 grams. These are the relationships for 1 mole, right? This is the relationship we established. Same thing for oxygen. For 1 mole of oxygen molecules, that's a compound because it's 2 O's, right? So you have 2 or more elements together, you have a compound. So there's 6.2 to the 23rd oxygen molecules in here. How much do they weigh? 32 grams. Why? Because it's 1 mole. And how much does 1 mole of oxygen gas weigh? Oxygen gas is O2. Remember, it's a diatomic molecule. So 16 times 2 is 32 grams. And then for carbon dioxide, same thing. 1 mole of carbon dioxide molecules has this many carbon dioxide molecules, and there's 44 grams in there. All right, the last thing we want to talk about is conservation mass. Total mass of reactants equals the total mass of products. That's always the case. So you have 2 moles of silver. They weigh 215.8 grams. You have sulfur, 32.1 grams, and then you have Ag2S, which weighs 247.9. So basically what this means, the total mass of the elements equals the total mass of the compound. So here's your balanced reaction. So I'm going to put how many moles of each you have. So you have 2 moles of silver, 1 mole of sulfur, 1 mole of silver sulfide. Add up the masses. 2 times 107.9 gives us the 215.8 we saw here. 1 times 32.07, there's a 32.7, the mass of this. And then 1 mole of this, 247.9 out, just add up the mass of the elements in the compound, right? 2 silvers, 1 sulfur. So notice, total mass of the reactants equals total mass of the products. That's conservation of mass. That is always the case. That's the reason we balance equations, because you have to make sure you have the equal masses of reactants and products. You can't have 240 here and 250 here. It doesn't work. Mass has to be conserved. So that was the mole in a nutshell.